Chapter 2, Circuit Elements. In this lecture, we will define a closed path, also known as a loop, and describe the behavior of voltage within a closed loop. Next, we will define Kirchhoff's voltage law and perform some example problems demonstrating how to use Kirchhoff's voltage law to analyze simple circuits. We are looking at objective number 2, which is to be able to state Kirchhoff's voltage law and be able to use this law to analyze simple circuits. A closed path is when we begin at an arbitrarily selected node. We trace a closed path in a circuit through selected basic circuit elements and return to the original node without passing through any intermediate node more than once. Notice in this circuit that all the closed paths follow either the clockwise direction or all follow the counterclockwise direction. You cannot have a mixture of the two directions within the same circuit. Once you establish a direction, you must continue with that direction. Also notice that we have a closed loop at the bottom of this circuit. Let's see. I was looking for the laser, but we don't have it. We could put a loop down at the bottom here if it is helpful for us to solve the problem. In this particular example, this loop was not necessary. Let's look at this circuit. It has two closed paths. And let me use a highlighter. So we've got a path here. Ooh, dear. Oh, my, I'm not very good with this highlighter. And we have a path here. A closed path. However, we do not have a closed path here. Nope. Well, let's erase all this. Okay. Why is the middle section not closed? Because there's nothing to close it here. We can redraw this circuit. Let's see, let's use black here, where it would look something like this. So we would have our voltage source here and the 6 ohm resistor here. And on this one we would have, let's see, our dependent source. So that would be a minus and a plus here. And then we'd have the 2 ohm resistor, and then we'd have the 3 ohm resistor. And this would be the 10 volt source. And this would be the 3IS dependent source. And I sub S, well, this would be I sub 0 here. And I sub S would be going this direction. Okay, so that's what this circuit would look like. I like these circuits. I think they're fun. All right. Kirchhoff's voltage law states that the algebraic sum of all the voltages around any closed path in a circuit equals 0. Let's look at this circuit. We have one closed loop. According to Kirchhoff's voltage law, we can sum up the voltages across each element and set the sum total to 0. Now I would like to talk about the standard convention used when labeling active circuit elements and passive circuit elements. For active circuit elements such as voltage sources and current sources, either independent or dependent, the standard convention is to use the active sign convention. So what is the active sign convention? That is when the current enters at the minus terminal and exits at the positive terminal. In this case, let's see. I'm not going to talk about how you label voltage yet. I think that's the next slide. For passive circuit elements such as capacitors, inductors, and resistors, we draw current entering the positive terminal and exiting at the negative terminal. Now, in this chapter, you will see problems which are labeled differently because the authors want you to think about this and to understand how to change the signs of current and voltage. So when we apply Kirchhoff's voltage law, when the current is passing through a voltage rise or oh, goodness gracious. What happened to my laser? So when the current is going from minus to plus, we apply a minus sign to our voltage value. So our voltage would be a minus. When the current is passing plus to minus, we apply a plus sign to the voltage value. So in this example, if I set my current in the clockwise direction, as I enter B sub S, this voltage source, I'm entering at the minus and exiting at the plus, so I would make B sub S a minus B sub S. And then as I move along this loop and I get to B sub L or R sub L, the current that I've drawn in here is entering at the plus terminal and exiting at the minus terminal. So V sub L will be a plus V sub L. Then as I move along to my R sub C circuit, I'm entering at the negative terminal and exiting at the positive. So R sub C or V sub C would be a negative V sub C. And lastly, as I enter, as the current enters circuit element R sub 1, I'm entering at the positive terminal and exiting at the negative terminal, so V sub 1 would have a positive value. So applying Kirchhoff's voltage law for this circuit would give me minus V sub S plus V sub L minus V sub C plus V sub 1 is equal to 0. Now let's use the same circuit but apply our current in the opposite direction. So this time it's in the counterclockwise direction. So at our source, V sub S, our current is entering at the positive terminal. And let's use the highlighter here. the positive terminal and it's exiting at the negative terminal. So that means that our voltage would be a positive. So it would be plus V sub S. And here, let's just put that in. Now let's go to R sub 1. We're entering at the negative terminal and exiting at the positive. So our voltage here would be negative, so that's minus V sub 1. At this R sub C, we're entering at the positive terminal, exiting at the negative. So our voltage would be plus V sub C. Then we come up to our next resistor, which is R sub L, and we're entering at the negative terminal and exiting at the positive, so it would be minus V sub L, and then we return to the beginning of our loop. So we set that equal to 0. All right. Okay. Let's do an example. Another example. Sum the voltages around each designated path in the circuit shown. All right. So in path A, our current is in the clockwise direction on all of these paths. So path A, we start at V sub 1. We're entering at the negative terminal and exiting at the positive, so it's a minus V sub 1. At the 2 ohm resistor, we're entering at the positive terminal, exiting at the negative terminal, so it's a plus V sub 2. At the 4 ohm resistor, we're entering at the positive terminal, exiting at the negative terminal, so it's a plus V sub 4. Then we have our voltage source here. We're entering at the minus terminal and exiting at the positive, so it's a minus V sub B. Then we move along to our next 3 ohm resistor, and we're entering at the negative terminal and exiting at the positive. So it is a minus V sub 3, and that is equal to 0. Now let's look at this path. We'll start here. We're entering at the negative terminal of the voltage source and exiting at the positive, so that would be minus V sub A. The 3 ohm resistor, we're entering at the positive, leaving at the negative, so that's plus V sub 3. The 5 ohm resistor, we're entering at the positive, exiting at the negative, so that would be plus V sub 5, and we completed the loop, so that is equal to 0. And let's look at loop C. Let's start at this voltage source. So we're entering at the negative and exiting at the positive. So that's minus V sub C. Then we enter at the minus terminal of the 6 ohm resistor and exit at the positive. So that's minus V sub 6. And the 5 ohm resistor, we're entering at the negative terminal, exiting at the positive terminal, so that's minus V sub 5. And the voltage source, we're entering at the positive terminal, exiting at the negative, so that's plus V sub B. And the 4 ohm resistor, we're entering at the negative terminal, exiting at the positive terminal, so that's minus V sub 4. And we've completed the loop, so that is equal to 0. And our last one. We'll start down here with this voltage source. We're entering at the negative, exiting at the positive, so that's minus V sub D. We come up here, enter at the negative, exit at the positive. That's minus V sub A. Come all the way up here to the 1 ohm resistor, enter at the negative, exit it at the positive. So that's minus V sub 1. Go to the 2 ohm resistor, enter at the positive terminal, exit at the negative, so that's plus V sub 2. And we head down to this voltage source. We're entering at the negative, exiting at the positive, so that's minus V sub C. And we come all the way down to the 7 ohm resistor. We enter at the positive terminal, exit at the negative terminal, so that is plus V sub 7. All right. Let's look at another example which applies Ohm's laws and Kirchhoff's current law and Kirchhoff's voltage law. Click on the link below to view this video. This is another problem, assessment problem 2.5, which uses Ohm's law and Kirchhoff's current and voltage laws to solve. Click on the link below to view this video. And assessment problem 2.6. Again, it uses Ohm's law, Kirchhoff's current law, and Kirchhoff's voltage law to solve for R, the value R. Click on the link below to watch this video. In this lecture, we defined a closed path or a loop. We located closed paths in several circuit examples. We then defined Kirchhoff's voltage law and performed an example problem using Kirchhoff's voltage law. Finally, we performed a few examples applying Ohm's law, Kirchhoff's current law, and Kirchhoff's voltage law. And this concludes this lecture.